What if I told you that the very fabric of the universe might be intertwined by an invisible quantum connection? For decades, we've understood gravitational waves, ripples in space-time, as purely classical phenomena, following Einstein's equations. But what if they're hiding a quantum secret? New research suggests that gravitational waves, the very same ones detected by LIGO, might exhibit quantum properties. If true, this could bring us one step closer to unifying general relativity and quantum mechanics, one of the greatest challenges in modern physics. Today, we'll dive into this groundbreaking discovery, explore its implications, and uncover how it could change everything we know about the universe. Gravitational waves were first predicted by Albert Einstein in 1916, but it took nearly a century before we could finally detect them. In 2015, the LIGO Observatory captured the first-ever evidence of these cosmic ripples, proving that space-time itself can stretch and compress when massive objects collide. These waves are generated by some of the most violent events in the universe: merging black holes, neutron-star collisions, and even the remnants of the Big Bang. They travel across the cosmos, carrying information about the cataclysmic forces that created them. Until now, scientists have treated gravitational waves as purely classical phenomena, meaning they behave in a predictable, continuous way, just like ripples on a pond. But what if that's not the whole story? What if these waves also possess a quantum nature, behaving more like tiny particles? New research is beginning to challenge our traditional understanding, and if it turns out to be true, it could reshape our entire view of gravity itself. For decades, physicists have struggled to reconcile two fundamental theories: Einstein's general relativity, which describes gravity on a cosmic scale, and quantum mechanics, which governs the tiniest particles in the universe. These two frameworks have remained separate until now. A groundbreaking study led by Dr. Partha Nandi and Dr. Bibas Ranin Mai proposes something extraordinary. Their research suggests that under certain conditions, gravitational waves may not just be classical ripples in space-time, but could also exhibit quantum behavior. One of the most striking implications of their model is the possibility of gravitational waves inducing quantum entanglement. This means that two objects, no matter how far apart, could become linked in such a way that a change in one instantly affects the other. This phenomenon, previously observed only in tiny particles, could now extend to the very fabric of the universe itself. If this hypothesis is correct, it would mean that space-time doesn't just curve and bend. It could also exist in discrete, quantized states. In other words, gravity itself might be a quantum force, carried by hypothetical particles called gravitons. This idea challenges everything we thought we knew about the nature of gravity. But how can we test it? Could we actually prove that gravitational waves behave like quantum particles? Proving that gravitational waves have quantum properties is no easy task. The detectors we currently use, like LIGO, are designed to measure tiny distortions in space-time caused by massive astrophysical events. However, they are not yet sensitive enough to detect the subtle quantum effects that may be hidden within these waves. To overcome this challenge, Dr. Nandi and Dr. Mai developed a theoretical model of a next-generation gravitational wave detector. This proposed system would include highly sensitive mirrors, suspended in such a way that they could detect not just the classical distortions of space-time, but also quantum-induced entanglement. In their model, classical gravitational waves cause predictable, continuous motions in the mirrors, just like how a passing wave moves a buoy in the ocean. However, if quantum gravitational waves exist, they could create synchronized oscillations in the mirrors, patterns that cannot be explained by classical physics alone. Imagine two distant wind chimes swaying in perfect harmony, not because of a shared breeze, but due to an invisible quantum connection. This would be one of the clearest experimental signatures of quantum gravity in action. Right now, our technology isn't advanced enough to detect these effects, but upcoming observatories, like LIGO India, set to become operational by 2030, could hold the key. By integrating quantum-enhanced measurement techniques, future detectors might be able to capture evidence of quantum gravitational waves for the first time in history. But if we do manage to prove that gravity operates at a quantum level, what would that mean for the future of physics? Could this discovery finally bridge the gap between Einstein's relativity and the strange world of quantum mechanics? If gravitational waves truly exhibit quantum behavior, it would be one of the most profound discoveries in modern physics. It would mean that gravity, the force that governs planets, stars, and galaxies, doesn't just bend space-time, but also operates under quantum rules at the smallest scales. This could finally help solve one of the greatest mysteries in science, the unification of general relativity and quantum mechanics. These two pillars of physics work perfectly in their own domains. Relativity explains the cosmos, while quantum mechanics governs the subatomic world. But they fundamentally contradict each other, leaving physicists searching for a deeper theory that connects them. A quantum theory of gravity could also shed light on some of the biggest cosmic enigmas. Dark matter and dark energy, which make up most of the universe's mass energy, remain largely unexplained. If gravity itself is a quantum phenomenon, it might offer new clues about these mysterious forces shaping the cosmos. Even more astonishing, detecting quantum gravitational waves could allow us to look back in time, all the way to the Big Bang. Unlike light, which can be scattered and absorbed, gravitational waves travel nearly unimpeded through space-time. If quantum properties can be detected in ancient gravitational waves, they could reveal secrets about how space-time emerged from the quantum vacuum and evolved into the universe we see today. The stakes are enormous. If these experiments succeed, they could revolutionize our understanding of black holes, cosmic inflation, and even the fundamental structure of reality itself. But the road ahead is long, and the technology to confirm these ideas is still in development. So, what comes next? How close are we to proving that quantum gravitational waves exist? And what advancements might accelerate this quest? The future of quantum gravitational wave research is incredibly exciting. With projects like LIGO India and advancements in quantum-enhanced measurement techniques, next-generation detectors will be equipped to study the quantum nature of space-time. These new detectors will push technological boundaries, using quantum sensors and innovative detection methods to catch the subtle effects of quantum gravitational waves. If successful, this could provide the first real evidence that gravity operates on both classical and quantum levels. Quantum technology is advancing rapidly, with breakthroughs in quantum computing, quantum cryptography, and quantum sensors. These developments are revolutionizing our ability to simulate quantum systems, secure communications, and detect minute fluctuations in gravity and other fields. As these quantum technologies evolve, they may provide the necessary tools to observe quantum gravitational waves. Collaborations between theoretical physicists and experimental scientists will be crucial to turn abstract ideas into real discoveries. Understanding quantum gravity could unlock new insights into astrophysics, from black holes to the early universe. The implications of this research are vast, and it could transform our understanding of the cosmos. So, what's next? We might be on the verge of a new era of discovery where space-time itself reveals its deepest secrets. Secrets that could change everything we know about the universe. As we wrap up, the discovery of quantum properties in gravitational waves could be a turning point in physics. It might not only bridge the gap between general relativity and quantum mechanics, but also open doors to understanding the universe in ways we've never imagined. The next steps in this research could reveal the very nature of space-time and gravity. potentially reshaping everything from black hole theories to our understanding of the Big Bang. We are just at the beginning of a journey that could change the future of science. If you enjoyed this deep dive into the quantum side of gravitational waves, be sure to like, subscribe, and stay tuned for more groundbreaking discoveries in the world of physics. See you next time.